Welcome to the second session of today, or the first session on Oblivious data access. Before we start, the rump session chairs would like to remind you that the deadline for the rump session submissions is at 1 p.m. So submit your best talks, announcement for jobs, or whatever you like until 1 p.m. and finish your slides in the lunch break, because now you have to, of course, listen to all these great talks that will be in this session. And the first talk is going to be about optimal single-server private information retrieval by Mingjun Zhu, Wei Kai Lin, Yanis Telekunis, and Elaine Shi. And Mingjun Zhu is going to give the talk.
Thanks for the introduction. I'm Mingjun Zhu. I'm a third-year PhD at CMU. This is a joint work with Wei Kai Lin, Yanis, Elaine. And today I'm going to talk about optimal single-server private information retrieval. So PIR, private information retrieval, it stands for public database and private query. Imagine that there is a client and a server, and the server stores a database of size n. And now the client wants to know for some particular index what is dbx. That means the value at the location x. And the privacy requirement says that the server cannot tell what exactly is the client's query x. There are many applications to this primitive. For example, you can build private DNS based on PIR. You can also build safe browsing or private contact discovery. And there are many other applications. In the classical model of PIR, there's no preprocessing, and we require the servers to store the database in plain text. So for example, if every location only stores a bit, then the server simply stores an n-bit string. Using fully homomorphic encryption, the best scheme can achieve polylog client time and polylog communication per query, but the server time will at least be linear in n. Can we hope for sublinear PIR in the classical model? Unfortunately, this is hopeless. There's a very important lower bound shown by Bimo, Ishad, and Malkin in their 2000 paper. They show that the server time has to be linear in this model. Luckily, in their paper, they propose a new model called a preprocessing model, and the preprocessing PIR can actually achieve sublinear query. This is the particular preprocessing model we care about today, and we call it the client-side preprocessing model. And there are other preprocessing models, but this is the one we're going to focus on today. So during the preprocessing time, the client will interact with the server, but notice that now the client doesn't know what will be the future queries. At the end of the preprocessing, the client is going to store some hints in its local storage, and using those local hints, the client can make multiple queries, and those queries can be made much more efficiently and actually sublinear. For the previous work, the best work can achieve actually square n online time per query, but they require square n communication. They are also assuming square n client storage, and they're using the LWE assumption. But the downside is they require square n communication per query. And we know that in classical PIR using FHE, you can actually achieve polylog communication. So can we hope for the best of both worlds? In our work, we actually show that it is actually okay to have the best of both worlds, and we actually show a single server preprocessing PIR scheme that has polylog communication, square n time, assuming square n client storage. And we are also using the LWE assumption. I want to mention that our trade-off between the online time and the client storage is actually optimal up to a polylog factor. This has been shown by a previous lower bound that the client time, the product of the client time and the storage has to be at least n. So our scheme is optimal up to a polylog factor. All right, so here's the roadmap today. Our idea to get the optimal single server PIR we will first construct an optimal two-server PIR scheme, then use fully homomorphic encryption to compile that two-server scheme to the one-server scheme. So in the two-server scheme, we assume that there are two non-colluding servers. They both store a copy of the database. And here, we assume that during the pre-processing phase, the client is only going to talk to one of the server. We call that the offline server. And during the online phase, the client is only going to talk to the online server. The idea here is that suppose we can wrap everything for the pre-processing phase into a fully homomorphic encryption scheme. And simply the client use the FHE scheme to encrypt all the messages it needs to send to the server. And now the server simply use fully homomorphic evaluation to generate those encrypted responses to the client. Because now everything is encrypted, it doesn't really matter whether it is the offline server or the online server, because the server simply learns nothing by the security of the FHE scheme. So using FHE, we can actually just simply replace the offline server with the online server, and now we have a single server scheme. But this transformation has two key requirements. First, it requires that the scheme has full separation property, which means that the client only talks to one server during the pre-processing phase, and the client talks only to the online server during the online phase. Secondly, we want efficient circuit representation for the FHE. Means that when you do the compilation, usually when we talk about the complexity of the algorithm, we think about that as under the RAM model. But when we are using fully homomorphic encryption, we usually need to evaluate the circuit. So when you do the compilation, there may be some overhead. So we want the pre-processing phase to have an efficient circuit representation. Unfortunately, the previous optimal two-server scheme cannot satisfy both of the requirements, so we cannot directly start from the previous scheme. We have to design a new two-server scheme. So in the next, I'm going to talk about our new optimal two-server PIR. So I'm going to first start from an inefficient strawman scheme, and then I'm going to show you the optimization we do to make it efficient, and finally, I'm going to highlight some of our proof ideas. So this is our two-server scheme. During the pre-processing phase, the client is going to sample m sets, m for m roughly like squared n log n. And for each set, the set will sample each index independently with probability 1 over squared n. So each set will contain roughly just squared n indices. The client simply sends all the sets to the offline server, and the offline server returns m bits. Those m bits denote the parity for S1 to Sm. When I say parity, it simply means the XOR sum of those database locations. And now the client simply stores those sets alongside with those parities in its local storage. And we think about those things as the hint. Why are those hints useful? Let's take a look. So when the client makes an online query X, it simply finds a set such that it contains X, and then it's going to resample the particular online query X in the set S. When we say resample, it simply means that we retoss the coin, and then we keep X with probability 1 over square n. So this is exactly the same as when we generate a set. And after we resample the set, we simply send this resampled set to the server, and the server returns the parity for this resampled set. And now we simply set the answer to be the parity of S XOR the parity of S prime. So why is this exactly just dbx? Well, because the resample process, we actually have high probability to remove X out of the set. So when that happens, the only difference between the set S and S prime is exactly X. So when we do the XOR, the result should actually be just dbx. Notice that this is not perfectly correct. So to get negligible error probability, we simply run k-parallel instances to reduce the error probability to be negligible. After we finish one query, we have to remove this consumed hint, otherwise the server is going to learn some private information. So the idea here is to refresh the hint. And the idea is that during the preprocessing phase, the client in addition stores squared n backup sets and those pair and their parities. And after it consumed a primary hint, it simply replaces it with a backup hint, for example, s prime prime. But we have to make sure that when we add the s prime prime to its primary hint, we need to manually add the online query x to the set s prime prime. This is because we want to maintain the local distribution of its primary set. Remember that we already consume a set that contains x. So when we do the refresh, we need to replace it with a set that contains x. That's the reason why we need to manually add x to the set. So this is our inefficient two-strawman scheme. It is actually efficient in its time. Remember that during the online phase, the client simply just find a set and then send the set to the server. And the server simply just compute the parity for that set. And every set, it has only size squared n. So the time is actually squared n per query. But it is actually inefficient in terms of its communication. Because every time you need to send a whole set, and the set contains squared n indices. So the communication should be squared n. And also the storage will be O(n). This is pretty bad because there are roughly squared n log n sets. Each set contains squared n indices. And now the optimization here is that we can actually improve the scheme. We notice that in the strawman scheme, we represent a set with square n bit. We simply just store all the indices. But actually, the idea here is to represent a set with a very short key because the set is actually random. So we can simply just use some kind of random seed and then expand this random seed to the set. And this is the similar idea from the previous work. What we need from the set representation? Well, from the server side, when the server sees that short seed, it should have a very fast set enumeration algorithm to expand the set. So we want this algorithm to run in squared n time. Also, remember that the client needs to find a set. So it needs to linearly scan over its local table. So we want the set representation to have very efficient membership testing algorithm. The idea is to write down every index using its binary representation. And then we think about the PRF. So we use pseudorandom function, and then given a key, we simply think about the key as the set seed. And then we simply use that PRF as the hash function. And then we hash all the prefixes longer than half log n to 0 or 1. And we only consider x to be in the set only when the half log n prefixes all hash to 1. It actually happens with exactly probability a half to the half log n. So that's exactly 1 over squared n. So why is this useful? Well, by definition, we can test whether an index belongs to the set very efficiently. You just have half log n PRF evaluations. We also have a very efficient set enumeration algorithm. I'm going to skip this part. This is still the same idea as before. But actually, in our single server scheme, we actually need two additional conditions. We need to have private resampling algorithm. Remember that the client needs to resample the particular online query in the set. So we actually need to do it in a privacy-preserving way. Otherwise, the server is going to learn your online query. Also, we need to have a private adding operation. Remember that in the local refresh, we have to manually add x to the set. And the private adding and the private resampling, so the combine of them is actually not supported before by our previous schemes. So our key new idea is to use privately programmable pseudorandom set. We construct this new primitive based on privately programmable PRF. So privately programmable pseudorandom function, it has the following syntax. So basically, given an upper bound L, we can generate some key K. And then we can actually program the key for some point value pairs. So after the programming, when you evaluate on the new key, if your evaluation point has been programmed before, then the new key will just output the program value. Otherwise, it's going to return the same value as before. And the privacy requirement says that the program key hides the program point. So using this programming very strong primitive, the private adding can be made pretty simple. So the idea here is simply just that we program all the prefixes relevant to that index. We simply program all the prefixes to be 1. So we have a new key, and then when we evaluate on this new key, all the prefixes will be forced to 1. And all the programming operation can be done in a privacy-preserving way. So this is how we do the private adding. And private resampling is pretty simple. We just resample all the prefixes. So that's the idea about how to construct a pretty efficient set representation. It has basically satisfied all the 4 conditions, and this is exactly our optimization in our paper. All right, so I want to highlight some of the proof in our paper. So we actually have 2 crypto primitives. We use the FHE, we also use the probably programmable PRF, and we also have some distribution analysis to do. To separate the crypto analysis from the probability analysis, we use a delay sample trick and to separate them. And if you're interested, you can take a look at the paper. We also derive a key lemma for the for the probably programmable PRF. We derive a lemma such that the programming operation can be considered as computationally indistinguishable from rejection sampling hybrids. So we use this key lemma to switch back and forth between hybrids and hybrids. So that's the highlight idea in our proof. Okay, so here's the final slides. So I just want to do a quick recap. So the idea from 2-server PIR to 1-server PIR in our paper, we simply use fully homomorphic encryption to simply wrap everything inside of the preprocessing phase. And the key requirement is that we want to have full separation and efficient circuit representation. And to satisfy both of the conditions, we derive an optimal 2-server PIR. The key idea is to design privately programmable pseudorandom set. And our PIR can achieve polylog communication, squared end time, assuming squared end storage, using LWE. And finally, I just want to quickly mention that we have, so the construction today is purely theoretical, but we have a new practical PIR work. It's available on ePrint. It's called Piano. It's still a single-server PIR scheme with sublinear server computation, but it sacrifices a little bit about the communication. It's actually squared end communication. But it's really fast. It can have, for 100 gigabyte database, 1.6 billion records. Our new work can have less than 40 millisecond online time. So that'll be it. Thanks everybody for listening.
So, are there any questions? Yes, maybe if you come to the microphone.
Thanks for the interesting talk. So I wonder, it seems that the sets, for the sets, you said that you want them to be random or pseudo-random, and it seems to be, at least naively, that it's an overkill. So maybe a weaker property of randomness suffices, and I wonder whether you looked at the possibility of replacing the PRF with some information theoretic generator, like, I don't know, low bias generator or something. It seems
that's
like
an interesting point.
square root n independence should suffice or something like this.
Yeah, that could be possible. I haven't thought about it very deeply, but for this construction, even if you replace the set representation with some IT secure one, you still need to still make computational assumption because you need to use
Sure,
FHE.
but when you want to evaluate this generator in the real world by an FHE, the circuit that you will get will be much simpler than, I don't know, an circuit or whatever you're going to use.
Yeah, it could be.
A simple polynomial representation.
Right. We haven't thought about it, but our new work doesn't really require those complicated things. So it's simpler. So if you want to take a look.
Thank you.
Thanks for the question. I saw there's one more question, maybe if it's very quick.
I just want to ask the proposal of the private programmable PRF. Is the proposal to hide the point, the key point, so the end point, so maybe you can use other tools like this?
What do you mean?
Okay. So the purpose of this is to hide the points, right?
Right.
Okay, I see. Thank you.
Okay.
Well then, let's thank the speaker again. And move over to the second talk, which is about weighted ORAM with applications to searchable symmetric encryption, which is by Leonard Assolin and Brice Minot. And Leonard is going to give the talk once everything is set up. Okay, take it away.
Thank you for the introduction. So yes, this is joint work with Brice Minot. So I'm going to talk about Oblivious RAM, which is a way for a client to exchange with a server and hide the access pattern of what they are exchanging. So to motivate, here is an example on how Oblivious RAM is actually used by the Signal messaging app. So let's say that Alice downloads the Signal app and she wants to check if her friend Bob also uses Signal. So she knows Bob's phone number, it's written below, and she is going to check with Signal's server if Bob's number is in their database. So every phone number is encrypted on the Signal server, and Alice can just make some queries on that. And for that, she's going to do a binary search. So so in green, this is the plain text numbers that she sees. And in red, it's going to be the encrypted data that the server sees. So she starts in the middle and does her binary search. So if it's lower than the middle value, she's going to the left and to the right, etc. And in the end, she finds Bob's number or she doesn't find it. So despite the fact that the phone numbers are encrypted, some information leaks because the server can guess what phone number Alice has accessed here. So what we want to do actually is to hide the access pattern. In that way, the server only sees that Alice makes a certain number of accesses, but the server cannot know what kind of computation Alice has made. Oblivious RAM is an old primitive. It was invented in the 80s, where the RAM meant actually a CPU exchanging with the RAM of the computer, but right now we are more considering a client exchanging with a server. And it's a simple couple of algorithms. First, a setup where we give the block size and the total size n of the objects that is going to be stored on the server. Then we get a client state and a server state. And we make some accesses to the server. An access consists of the operation that we're doing, either a read or a write, the address of the object we're accessing, and eventually some data if we are making a write. All of this is, of course, hidden from the server because we also want to hide whether we read or we write a value. The security definition for that is indistinguishability between two sequences of accesses. So two sequences of the same size should remain hidden, whatever the contents of the actual accesses are. But proving security is actually the easy part, because as we are going to see, it's easy to see that the access pattern is information theoretically hidden. The challenge is going to prove correctness, meaning that we actually execute the RAM without any failure. So in this work, our goal is to have an Oblivious RAM that handles many objects of different sizes without changing the communication cost of the existing ORAM constructions. A naive solution would be to pad to the largest object size, but this is bad because you're actually paying the largest object size every time you make an access, and you don't really handle that many objects. What you could also do is to divide big objects into smaller chunks, but then you're paying because you need to make many accesses, so this is bad as well. What we want to do is to have an ORAM of total size n that handles more than n objects, each of a certain weight wi, such that the sum total of the weights is going to be less than the total that the server can handle, and each weight is going to be less than some elementary weight 1. As long as that constraint is respected, we can have the ORAM be what we call dynamic. So when we overwrite an object, its weight can change. And this is what we call a weighted Oblivious RAM. So there are many different ORAM paradigms. In this work, we're going to be focusing on 3 ORAMs. This is the main result of this work. But we also have results that prove that any ORAM can be made to accommodate objects of variable sizes with a small blow-up in the communication cost. So next I'm going to present Path ORAM, which is the most widely used ORAM. Signal uses this type of protocol for their application. Then I'm going to explain and prove and sketch the proof of the main theorem of our work, which is to give a general transformation from a trioram, a standard trioram, to a weighted trioram, and explain how we can, what criterion a trioram needs to have to handle such a transformation. So the idea of Path ORAM is to have n objects, so the original triorams, right, the standard one. We store n objects in buckets. Each bucket can handle at most z objects. The buckets are in a binary tree of that log n, and each block is going to be associated with a leaf. So when we access a block, we don't know its exact position in the ORAM, we just know on which path it is. Path from root to a leaf, which is why it's called Path ORAM. Let's say I want to access the orange block here, and I know that it is associated with leaf 2. This means that when I access the server, I only know that on the green path, the block I want to access is on this green path. And what I do is simply go up the path from leaf to root and download every bucket. So first I'm downloading the bottom bucket, then the middle one, then the upper one. And once I have done that, I have seen where the block I wanted to access is, so I can read it, modify it, maybe if it's right, and I re-encrypt it. And then what I'm going to do is to write back everything on the same green path. But now that I've re-encrypted my block, so the one that was orange is now gray, I also pick uniformly at random a new leaf for it. So let's say I pick leaf 3. Now this block needs to be on the path from root to leaf 3. But I'm writing back on the green path, so I need to write it back at the intersection of the path somewhere. So here, since it's step 3, I can only write it back at the root. So this is what I'm doing. I'm just writing back my blocks. Then I write back another block. But as I said, the buckets have a fixed size. So what if at some point I run out of space? Well, the client has an offline memory that we call the stash. And the stash in Path ORAM is of size small omega of log n. And this is where we store the blocks that we cannot write back online. So I'm writing back the block I couldn't. And as I said, it's easy to see that it's secure because when I access a block, I reveal to the server the path on which this block was. But anytime I do that, immediately after, I pick a new leaf that remains secret, and I write back the block on the path of this new leaf. So the path where the block remains secret at all times after every step after every access for the server. What is important is to prove correctness, and in the case of Path ORAM, is to prove that the stash never overflows with overwhelming probability. So from the path theorem paper, we know that the probability that the stash load is greater than some value r is exponentially low in r. So this is why we need to have something slightly bigger than log n for the probability of an overflow to be negligible. Our contribution is to show how to handle blocks of variable sizes. So here is how we are going to modify a theorem to become a weighted theorem. Let's say that we have m blocks, m greater than n, and each block is of size less than b. So you can see b as being 1, but this is being as the number of bits for a block. The sum total of the weights needs to be equal or less than n times b. And we're going to modify how the buckets behave. Now we are going to say that we can store blocks in the bucket until they reach the threshold z. So I can store a small block, a bigger block, a smaller block, and at some point when I reach that threshold, I say that this bucket is full. So I cannot store objects here anymore, and I need to either go up a level in the tree, or if I'm already at the root, things go back to the stash. So the main theorem is, if we have a Theorem protocol where we read when we read buckets, it's done via a Theorem, which means that we download the entire bucket. We are not trying to do anything clever to access only the block that we want. The stash load comes from a collection of subsets of buckets in the infinite RAM, which is an idealized RAM model that helps us for the proof that I'm going to show you in the next slide. Then we show that the overflow is negligible, and this ORAM can become a weighted ORAM. So the proof. Consider a sequence of accesses S, and we're going to consider the execution on the infinite ORAM, where we assume that the buckets have an infinite size. We can store as many objects as we want in the bucket. We are going to transform this idealized ORAM into a real one, show that it has the same stash load as our real ORAM, and show that this stash load is negligible. And then in that case, it's going to show that the probability of an overflow is negligible in our real case too, and so we're going to have ourselves a weighted ORAM. So this is the state of the infinite ORAM after the execution. You can see we have the bottom left bucket, which is overflowing, and it's not possible that this happens in the real ORAM. So we're going to transform that state into a real state by just cutting everything that sticks out. And then we're going to try and put it up in the tree. So here we have some space on the upper levels bucket. So we're going to cut another chunk of this block, put it here. But now I don't have any more space in my tree. So what am I going to do with the remaining block? Put it in the stash. And this is where the stash load after post-processing comes from. And we can notice that the stash load of the post-processed ORAM here is greater than the stash load of the real ORAM, because we're not even allowing to have something stick out a little. Everything just goes to the stash. So now let's call x of w, where w is the weight distribution vector of our objects. xw is the random variable of the max stash load in the post-process infinite ORAM for any permutation of w. So xw is the worst case stash load that the ORAM can have. We're going to show that the expected value of this stash load is going to be less than the expected value of the stash load in the standard ORAM. Okay? U here means that we have n objects of size 1, and that's it. So this is the standard case. To prove that, we use what we call a majorization argument. So let's have two vectors v and w of the same sum total weight. And when we sort them in decreasing order, we say that V majorizes W if the partial sums of V are always greater than the partial sums of W. So you can see here a graphical representation of what majorization might look like. And we have a lemma that says that if I have a short convex function, which means that it's convex and it's symmetrical, so for any permutation of a vector V, the value of f is the same, then this function is going to take point the slide. The function is going to preserve the majorization order. So if V majorizes W, f of V is greater than f of W. Now we can notice that our variable x is short convex, because so it's easy to see that it's convex, and by definition, whatever the permutation is going to be the same value. The expectation function is convex, and U majorizes any weight vector, which is easy to see in the figure here. Well, from that, we know that the expected value x of W is less than the expected value of x of U, thanks to our lemma. And thus, since we know from the Theorem paper that the expected value of x of U is negligible, the expected overflow is also negligible. We have some experimental results that show that actually, the standard theorem is the worst case. So you can see that the stash load is always, the maximum observed stash load is always lower than the maximum for the standard theorem. So the takeaway from my talk is that three theorems are powerful enough to, without any added cost, handle weighted objects. And we give a criterion to prove that which theorem is able to handle weighted objects. Now, any theorem can actually handle them, but we need to have some communication cost blow-up. And if you check our paper, you can see how weighted theorems can be used to build searchable symmetric encryption. Thank you very much.
Leonard, thanks for the talk. Are there any questions in the audience? Yes, can you please come to the microphone?
Thank you for the nice talk. I'm just wondering if your technique, like the sure convex argument, work also for other similar primitives, say private information retrieval. Have you think about that?
So that's a good question. So I would need to learn a bit more about PIR to know if this type of argument could work. But this is a very powerful tool to use majorization and short convex functions, and it's been used in a few articles, but it mainly comes from the combinatorics community, and I haven't seen that used a lot in cryptography papers, but it certainly would be of use to consider these arguments.
Okay. I think in the interest of time, if there are any other questions, maybe ask the speaker in the break. So let's thank the speaker again. And the last talk of the session is going to be about nanogram, which is garbled RAM with overlock and overhead, and it's work by Andrew Park, Wei Kai Lin, and Elaine Shi, and Andrew is going to give the talk.
Hi everyone, I'm Andrew Park. I'm a second-year grad student at CMU, and I'll be giving a talk on our work, nanogram garbled RAM with O tilde log n overhead. And this is based on joint work with Wei Kai Lin and my advisor, Elaine Shi. So before we can talk about garbled RAM, we have to remind ourselves about garbled circuits. So as you guys may know, in a garbled circuit model, we have a garbler and an evaluator. So we have two parties that wish to compute some joint function on their private input data. The most important property of garbled circuits for us is the fact that it's non-interactive. The garbler can basically garble their input as well as the circuit and pass it over to the evaluator. And the evaluator locally can do all of the computation and then pass the result back to the garbler. However, as we know, most of our computation is done in the RAM model, which is sort of incompatible with the circuit model. And particularly, because we're working in the circuit model, there's this large RAM to circuit conversion whenever we have to do anything with the RAM. So in particular, if the RAM is very large, because we have to unroll the memory for every single RAM access, we're going to have a very large circuit blow up in the size of the RAM. Because of this, there was this new primitive called garbled RAM that was introduced in 2013 by Liu and Ostrowski. And in this model, rather than just having a circuit that computes everything, we're trying to construct this thing called an access gate. And what an access gate does is it's basically a random access where the input is some garbled index I, and the output is the value that is at that index. So you can see that this is going to be very hard because the evaluator sort of needs to, on the fly, do a dynamic access, even though the garbler does not know anything about the access at the time of the garbling. And in particular, our goal is that the access is going to take time in a sublinear blowup in the size of the RAM. So obviously, if we allow a linear blowup, then that's the same thing as just unrolling out the entire memory. So now I'll briefly lay out the landscape of prior garbled RAM constructions. So the first couple of garbled RAM constructions all had blowup in polynomial in the security parameter and polylog in the size of the RAM. However, all of these constructions are very impractical, and in particular, they require a non-black box use of PRF evaluations inside of the garbled RAM. Last year, as you may know, there was this new construction introduced called epigram by Heath et al. And this construction had blow up log squared in the size of the memory, and this is pretty practical. And then here, it's important to recognize that there is some lower bounds. So if we think about what is the best possible that we can do, we can think about having some ORM such as circuit ORM and garbling a standard tree ORM. And then think about what the blowup is. And as we know from the ORM literature, this will cause a blowup of logarithmic in the size of the RAM. However, this is going to require interactions. So this seems to be a standard lower bound for our garbled RAM problem as well. So here in this work, we ask, can we have a non-interactive garbled RAM scheme which asymptotic performance is competitive to the interactive state of the art? So in this work, we introduced nanogram, which has O tilde of log n overhead, where the tilde is hiding polylog log factors. And as we can see, this is near optimal dependence on n, so because of this log n lower bound. Okay, so for the outline of the rest of the talk, I'll first introduce the language translation problem, which is the crux of the garbled RAM problem. Then I'll introduce the strawman scheme, which is just garbling a standard ORM tree. And then finally, I'll discuss our techniques, which allow us to achieve this polylog log overhead. Okay, so first I'll introduce the language problem. So in the language translation problem, if we think about the garbled circuit, we can think about every single garbled circuit gate speaking some time-dependent language. So in particular, if we think about the input to the gate, we require that this data is being encoded under some time-dependent label, so in this case it is this orange L, so that it is able to be read and processed by that gate. So here, if we think about the garbled circuit as being a bunch of sequential time-dependent gates, every gate is expecting an input garbled under its time-dependent language. So in particular, if we're in this garbled RAM model, that means that if we want to do an access for some random xi at a time-dependent gate, so here at t equals 1, it is expecting some random element xi garbled under the language for t equals 1. Somehow the garbler needs to prepare for this in advance, even though the garbler does not know what xi will be at t equals 1. Right? So the garbler here does not know what I is in advance, and similarly, the evaluator does not know at what time t xi is going to be retrieved. So this is clearly an incompatibility here. So our goal is somehow we need a way for the evaluator to locally translate xi under the time-dependent label LT. So now I'll talk about a strawman scheme, which is just garbling an ORM tree. So as we saw in the previous talk, if we just have a garbled ORM tree and then garble it, we know that some access is going to lie on some random path, right? And this random path is allowed to be shown in the clear since it's a uniformly random value. So here, if we think about each node as being some garbled data structure and every node having a local clock, what we can do is we can sort of pass the time-dependent label down this random path in the tree, and the labels are garbled in advance so that you are able to read from each bucket. Right, so if we have this time-dependent label and we know that xi is laying on this path due to the path invariant of the ORM tree, our goal is to route these labels as well as LT down this path, and we're guaranteed at some point to be able to do the translation of xi under LT using these logarithmic labels. So now you may be asking how we're going to actually pass down these label payloads down the tree. And we use this gadget called the garble switch, which was introduced in the prior work. And this garble switch basically is a gadget that allows for dynamic language translation. So now I'll discuss the garble switch. In our garble switch, there is a parent node as well as two child nodes, and each of these nodes has its own local clock. So you can think about the local clock as being the number of times the garbled data structure has been invoked. So that means that this is actually a dynamic value, and the garbler does not know what this time is going to be in advance. So when it's invoked, the local time is going to increment. So in this example here, the parent node has been invoked 5 times, and then 3 have been passed to the left and 2 have been passed to the right. So every node is keeping track of its own local time. And here it's important to note that for the parent root node, the parent local time is actually just equivalent to the global time, since the root node is going to be invoked at every time in the computation. So as we're passing down the data payload down the tree, the garbled payload must speak the local time-dependent language of that node. Right, so here, for example, if we think about the orange node, since the orange node has already been invoked 3 times, at the next invocation, it's going to expect the payload to be translated into some language L4. So to do this, what we can do is we can prepare 2 garble stacks of languages, and this was introduced in the prior work. So here we can prepare for 4 accesses on the left and 4 accesses on the right. And note that the garbler in advance does know how many times each of the children are going to be invoked, although he does not know at what time-dependent time is going to actually be invoked, right? So when we receive some value of the data payload as well as the leaf address at which is going to be passed down, so here assume that the data is going to be passed to the left. What the parent node can do is it's going to do a real pop off of the left stack, and it's going to do a fake pop off the right stack. So here, using the fake pop is just going to output a garbling of 0, while the real pop is going to output the language for which the payload needs to be translated into. Now, using this garbled language value, what the parent node can do is he can translate the data payload into the compatible language for the child, and then pass that translated value down to the child. And then that child is going to recursively do that all the way down the tree, logarithmic number of times. The important thing to note here, and this is the main source of overhead for the prior work, is that the cost of doing a pop from this garble stack is logarithmic in the size of the stack. So, for example, in the root node, because the root node has a provision for n accesses, the cost of this root node is going to be log n. So now I'll briefly discuss our techniques. So there's 2 main sources of inefficiencies here. The first is the fact that there's very large switches that have to provision for a large number of accesses. So for example, as we just discussed for the root node, because the root node needs to provision for n accesses, that means that there's going to be a log n overhead on the root node. And similarly, for the second layer of nodes, they have to each prepare for n over 2 and then n over 4, etc. So this is going to cause very large switches in this scheme. And that's actually the main source of overhead for the prior work. Second, we must pass a very large payload length all the way down the tree, and in particular, we have to pass a logarithmic number of labels, and each label is of size in the security parameter. And note that we have to pass the log number of labels because we have to do a read from all of the buckets, and this is inherent in the ORM tree construction. So our contributions are as follows. The first is we have, using prior work and basically some insights from bucket ORM construction, we're able to break up the switches into polylog size switches. And this allows us to actually break down the log n overhead from prior work into polylog log. And that's where we are getting some of our savings. Second, instead of passing a large payload length, namely the logarithmic number of labels, we used an XOR trick that allows us to only pass a single label. So this allows us to reduce the overhead by a log factor. And you can see our paper for that insight. So now I'll discuss our intuition behind breaking up the buckets for the large switches. So our intuition is as follows. Basically, for any of the large switches, what we want to do is break them down into switches of smaller size. And what we realize is that we can associate each of the larger switches with an exponentially growing number of buckets and switches. So if we have an ORM tree as follows like this, what we can do is break down each of the buckets into a logarithmic size. And use a static rebuilding operation in order to make sure that the bucket is always provisioned with enough labels for it to actually do the computation. So here, what we see is that on the lowest level, which is the root node is going to be rebuilt on every time step. On the second layer, it's going to be rebuilt every 2 time steps, and on the third layer, every 4 time steps, and so on and so forth up the tree. So we see that the rebuilding is being done in a hierarchical manner up the tree, and that allows us to break down the bucket and switch sizes of each of the levels to the same size. So here, instead of having a linear-sized switch that we saw in the strawman scheme, each of these switches here are only of each of the buckets here are only of size logarithmic, and this is due to insights from the bucket ORM work. So now we have an idea of how to break down the bucket into these smaller sizes. So now we need to have some rebuild operation that allows us to actually do the refreshing and reinitialization of the buckets on every time step. So what we see here is that if we had all of the buckets on the first and second levels full, every b time steps, where b is the size of the stash, what we'll do is use a hierarchical rebuild style operation and use that in order to do the rebuilding of the tree. So for example, here, if both the first and the second levels are filled, what we're going to do is rebuild these buckets into the third level. And this is going to happen every b time steps. So it's very similar to a hierarchical rebuild structure. So you might think that here we are done because we have all our smaller buckets and we have our rebuilding operation that allows us to do the rebuilding of the tree. However, there is still an issue, and this is due to the fact that the rebuilds are actually being dynamic. So although the rebuilds are dynamic, so although we're able to provision for the buckets at a static time schedule, we still do not, the garbler still does not know what the axes are going to be at garbling time. So here's an example. Imagine the buckets are filled on the first and third level, and we're doing a rebuild of the first level into the second. These children have advanced to some unknown local unknown local time, because we do not actually know how many accesses went to the left and how many accesses went to the right. And there's no way for the garbler to actually account for this in advance, because these are random accesses. So our solution is to equip all of our garble data structures with finalized routines that allow us to actually prepare the garble state required in order to pass the necessary information up the tree for the evaluator to actually do the reinitialization locally. So note that we can actually not use any of the garbled data structures that were designed in any of the prior work in our scheme directly because of this finalization. So rather than doing the rebuild directly, what we can do is equip all of our data structures with this finalized routine. So here, the parent node is going to run the finalized routine at the time of the rebuild. And this will allow the parent node to prepare the garble state required and pass these down to the children. And this will allow the children to actually prepare the necessary state in order to fully reinitialize the buckets and the switches on that level. So there's a bunch of other, so this was a very high-level overview of our construction, so please see our paper for a more formal treatment. But we also have many other additional optimizations that allows us to design a practical garbled RAM scheme. So for example, we have a way of avoiding a security parameter blow-up when we do our garbling scheme based on depending on what we know about the input. Second, we have a nice modular framework that allows us to actually compose our proofs for the garbled data structures in a nice modular way. And finally, we have other practical optimizations, particularly with our use of the buckets and the garble switches that allows us to achieve more practical performance. So finally, I want to end with a graph of the concrete performance here. So here the orange line is a linear scan, so that would just be the naive strawman of doing the linear scan across the RAM. And the blue line here is the prior work. So you see that as the size of our memory grows larger, we are actually able to achieve better performance than the prior work, and we do consider this to be practical. So so we're actually considering building out this garbled RAM scheme and trying to find some nice applications for it in practice. So with that, I will end and take any questions. Thank you.
Thanks for the talk, Andrew. Are there questions in the audience? So since you're thinking about actually implementing this, so what are the roadblocks that are in the way for doing this?
So I think one of the hardest things is the fact that the evaluator actually needs to do all of the wire soldering at runtime. So as we know, in most garble circuit constructions, the garbler actually prepares all of the gates in a sequential order for the evaluator, and the evaluator just needs to feed it in and finds the output. So here, the evaluator actually needs to do the soldering by themselves, right? So we're only preparing the data structures for them, and then they actually have to connect them all together. So that's actually pretty difficult when we're trying to actually consider the implementation. Yeah.
Thanks. So let's thank the speaker again, and you have a short 10-minute break to switch tracks.